session of today. And I have a great pleasure to introduce Brian Connery, who will talk about twisted moments. You're welcome.
Thank you, Kaisa. Yeah, thank you for the invitation to speak and for this nice occasion of Balu's 70th birthday. Wow, that sounds like that's getting up there. I guess we'll all get there soon. Some of us sooner than later. Anyway, I first met Balu back in, I believe it was 1981 in Urbana. So we're talking 40 years ago. Is that right? You were there, Balu, the 81, 82 academic year in Urbana? Or was it 80, 81? It was 81, 82, right?
Yes, yes.
Yeah, 81, 82. And yeah, he had just recently done his very nice work on the error term in the second moment of the Riemann zeta function. And I was working on zeta function too. So I was very excited to have him. I was at Illinois from Urbana from 80 to 82. So I was very happy that he was going to be there as well. And so that was quite nice. And so we managed to do some work together. And that work is going to sort of form the basis for this talk, which I've called Twisted Moments. Now, I'm going to attempt to do it's mostly just in slides, but I thought I would try to do some writing as well. And let me see if I can manage that just to get warmed up here. And so let's see if this works here. So let's see. So what do we mean by twisted moments? So I'm going to be interested in things like integral 0 to t, zeta half plus it squared, and then times, say, m over n to the it dt. So that would be an example of a twisted moment, or sum over chi mod q for primitive chi's, maybe something like L half chi squared times chi of m for some integer m. So everybody can see this okay and hear me okay? Yeah.
Yes.
It's fine. Okay. Right. Or maybe if you had maybe if you're summing over say fundamental discriminants, maybe L half chi d quadratic characters, maybe the first power or the second power times chi d of say some L, or maybe you're summing over f in some space of new forms, hk of q, something like that, and then you have maybe summing with the harmonic weight L half f, again, to maybe to some power, and then times lambda f of L. So these are kind of the situations that'll come up in the talk. And so these are your moments, but they're twisted by, one of the Dirichlet series coefficients, or maybe two of them that are in your family. So here we might have chi of m. I should put maybe chi of m, chi bar of n, more analogous to the zeta function case. And after we know now, we sort of attach a symmetry type to different families, sort of based on what we know from random matrix theory and from work of Katz, Sarnak, and things. And so these would be unitary examples, and this would be symplectic, and this would be orthogonal. And we know that the statistics of the families, like the large values, the moments, the way the zeros behave, things like that, are dictated mainly by the symmetry type, but also to a certain and to a lesser extent by the actual family. Mostly the actual family gives you sort of differences in arithmetic constants that can arise, especially to do with large values and moments. But the main sort of statistics are really dictated by these symmetry types. Anyway, so this is going to be the subject of the talk, and I'm interested in this for several reasons. One, if you want to study zeros, then you usually, zeros are either zeros or non-vanishing. Then quite often you'll look at moments of L functions times a mollifier. That means times an auxiliary polynomial that's multiplied on that has coefficients that kind of imitate the inverse of the zeta function or the L function. So they have, in particular, they have Mobius sort of coefficients in there. And if you're looking at large values, then again, you want to do moments multiplied by a polynomial, but now you want to sort of amplify the large values. And so you take coefficients of your auxiliary polynomial that would sort of make the large values, kind of exaggerate the large values, and that enables you to study, subconvexity, things like that. Okay, so now, so here's, so I want to just show you some pages from the paper that we wrote in Urbana back in 1981. So Heath Brown actually came over and visited at the same time. I think he was only there for a month or 6 weeks or something, but we got him involved in this project as well. And this is right after my thesis, which I had worked on Levinson's method. And well, like I said, for studying zeros, I was interested in zeros, critical zeros on the half line. And so an important thing was to be able to do complicated integrals like the one here, the integral of zeta, mod zeta squared on the half line multiplied by an auxiliary, a Dirichlet polynomial, in this case of with coefficients little a of m, and the length of the polynomial is capital M. And like I said, for studying zeros, you want to look at mollifying. So your A of M will be mu of M or mu of M times some kind of smoothing polynomial. And you don't, in Levinson's method, you don't actually integrate on the half line. You need to put in little shifts, integrate slightly off the half line, and to be able to carry out his method. But what turns out to be absolutely critical in these calculations is the length of the polynomial. So how big can you make M? And so the whole thing is to try and make M as big as you can. And so that's the goal. Anyway, so we studied this with that in mind, trying to be able to get a large M. Now in Levinson's method really worked for M equals t to the 1/2. So that's sort of the kind of natural place to go. I mean, there have been earlier works, Selberg and things like that, but before Levinson, it hadn't really been critical to try and get a large value of M. And so he worked hard at that, and kind of the natural thing that comes out is that you can take M as around square root of t to the 1/2 minus epsilon. So we studied this just sort of in general with general coefficients, and we came up with this theorem that here's a formula for what that integral looks like. So we're calling I is that integral, and our theorem is that I is equal to this sort of combination of this sort of bilinear form in the A's. You have a GCD, and you have log and 2 gamma, and then an error term script E, which is sort of in 2 pieces. One of the pieces, E1, is just t over a large any power you like of log. So that's sort of fine. And for arbitrary coefficients, E2 is can be bounded by m squared times t to the epsilon, which indicates that the size of I is around t, or depending on what the a's are, t or t log t or something like that. In general, we have m squared t to the epsilon. That more or less corresponds to Levinson, what Levinson did. And we just have this sort of for general coefficients. And then if something called Hooley's R star conjecture is true, then in general, you can get up to, you get an error term m to the 7/4 times t to the epsilon, which means you could take m equals t to the 4/7. So that would be a little bit bigger. And R star, let me see if this works. R star is something like summation R less than or equal to x e of, let's see, I haven't thought about this. I'm probably going to get it wrong, but something like if you sum R bar is the inverse of R mod Q, so sum over R and Q co-prime up to X, then basically you get square root of cancellation right away. Maybe you can put another variable in here. Anyway, that's the R star conjecture. So it's about cancellation of incomplete Kloosterman sums that you get square root cancellation right away. Very difficult question. And then this was sort of the main point was this next line that if A of m has the shape mu of m times a smooth function f, then we could get E2 is m to the 17/12 times t to the 1/4, which turns out to give you then an asymptotic formula in the case that that t goes up to 9/17. And the whole point was to try and beat 1/2. And so we did using sort of Vaughn's identity or Heath Brown's identity, whoever's identity you want to call it, for Mobius was kind of a key part of that thing. And then bounds for Kloosterman sums. Well, the Weil bound comes into this whole thing. But we conjectured something which so then this D here is in the case that AM equals 1, well, then you can actually just use your knowledge of the fourth moment of zeta to prove that that formula is actually correct with m all the way up to t to the 1 minus delta. So that's a simple example where you just take AM equals 1, where in fact our formula works for m all the way up to t to the 1 minus anything. And so we made a conjecture. That in fact that our formula should hold no matter what AM is, all the way up to t to the 1 minus delta. And also, we noted that in the case AM equals 1, that the formula fails once m goes past t. So if m is t to the 1 plus delta, then the formula is no longer true. The average changes its shape once m passes t in general. But anyway, so we have this nice conjecture here, and it would be good to prove that conjecture because, among other things, it would imply Lindelof hypothesis. If anybody wants to interrupt any time and ask any questions or make any comments, please feel free to. I don't mind. Just speak up. As a corollary, you take AM as mu of m times 1 minus log m over log big M. So mollifying the zeta, you really need to have a smoothing factor in here. If you just put a mu, you don't get such nice results. But if you have a smooth factor here, then you get this sort of nice if m is sort of t to the theta, then you have 1 plus 1 over theta. And so you can sort of visibly see that as m grows, this decreases. And ideally, what you would like would be to have m go to infinity. And then you would sort of get perfect, kind of mollification of zeta and have the integral of zeta times this thing really is getting close to t. And so that would be nice. We gave an explicit bound for the sum of the distances. You take all the zeros that are to the right of a half up to height t, and the total sum of the horizontal distances is less than 0.085 times t. And then so here we mentioned the application of to zeros. Now we didn't work our formula out for all of the with the shifts that were needed that would have allowed us to do to apply this to Levinson method, but that was really just a technical thing that we could have done easily. And you see, if so, the when m is t to the 1/2, you can get 36% of the zeros on the half line, and with the 17/9 that the three of us got, we could have got, if we'd worked out the details, we would have had 38%. So morally, we had 38% of the zeros. And if Hooley's R star conjecture was assumed, then you could get up to 40%. And from our conjecture, you would get up to more than most of the zeros, 50%. Okay. All right. So a few years after that, I used the work of Desier and Ibanez, and actually could get extended the range to m equals t to the 4/7. That's in the case of mu, not in general. So it's mu of m times smooth. Okay, and then with that, then was able to get 40% of the zeros on the half line. And then that's been improved a couple times since then. The current record is 5/12 by those four authors: Pratt, Robles, Zaharescu, and Seindler. Now, that question I sort of highlighted a second ago, can in that one formula, could you let m go to infinity? Well, in the case that am equals mu of m, with capital M as t to the theta, David Farmer made the conjecture that, so we had observed that you can take, it doesn't work to take m bigger than t for any set of coefficients am, but in the special case mu of m, he made the conjecture that you could take theta as big as you wanted and still get still maintain that the asymptotic formula that comes out. So the conjecture that we had now for, but in the case am equals mu of m, you can take as big a theta as you want. And then he called that or it became known as the theta equals infinity conjecture. It was the thing that led him to originally to make the original kind of beginning conjectures, the ratios conjectures for like averaging 2 zetas over 2 zetas, like doing an average of integral 0 to t zeta half plus alpha plus it zeta half plus beta minus it over zeta half plus gamma plus it, not a 0, zeta half plus delta minus it dt. So a conjecture, so this would be the ratios. And David made a conjecture for how this thing should behave, at least the main term of it. And that is sort of began the study of ratios and the ratios conjecture. Another kind of nice thing is that the theta equals infinity conjecture. So morally, we thought, oh, that needs to imply RH because you're getting sort of perfect mollification, right? As I mentioned, when theta gets larger and larger. But to actually nail that down, it takes a little bit of work. And Sandro Bettine and Steve Gonick showed that. And then later, Sandro and Fai-Chandi and Max Rajivi proved that for arbitrary coefficients, you can take your m slightly larger than t to the 1/2 arbitrarily. So this is sort of 1/2 plus, I think it's 1/66 is what they got, just in general for any old coefficient a of m. So that was kind of nice. The t to the 4/7 that I mentioned at the top of this screen, using results of Desier and Iwaniec, one of the things was that one of the ingredients was actually the average of a fourth moment of zeta times an auxiliary polynomial of, this is in this case of length t to the 1/5. They proved an upper bound for that using their famous work from Inventiones. And that was a key ingredient that allowed us to get up to, or allowed to get up to t to the 4/7 in the zeta squared case. Nigel Watt improved that t to the 1/5 to t to the 1/4. And these are upper bounds. And then Chris Hughes and Matt Young gave an asymptotic formula for that, for an arbitrary polynomial of length t to the 1/11. And in very recent work, Sandro Fai, Zhenan Li, and Maxime Rajivi now have an asymptotic formula for integral zeta to the 4th times m squared with arbitrary coefficients that works all the way up to m equals t to the 1/4. So it's quite nice, quite a nice piece of work. And one would think that should lead to improvements for zeros on the of zeta on the critical line, but so far it hasn't played. I mean, despite the fact that the original Desier-Iwaniec was so important, this hasn't played quite as significant a role. And but it may just be because nobody's figured out a good way to use it, and so it would be nice to try and do that. In 2018, the CIS, that's me and Iwaniec and Sound, their origin, using the something we call the asymptotic large sieve, we're able to do the analog of actually prove the conjecture from that original paper of Balu and myself and Heath Brown. In the case when you average over Q as well. So this would be sum over Q less than Q, sum over chi star primitive mod Q L of 1/2 chi squared times sum m less than or equal to m chi of m a of m squared. We proved the analog of that formula for m all the way up to m can go up to q to the 1 minus delta for any delta. So it's actually true there. And that has some nice applications. One is that we can now say that at least 60% on average of zeros of Dirichlet L functions on the critical line. So you average over all the Dirichlet L functions, mod all the primitive L functions, ls chi mod q primitive, and q up to big Q. Take that whole collection of around big Q squared L functions, and count all their, count how many zeros they have up to, well, a pretty small height, but it's a height that's increasing with Q. And at least 60% out of that collection of all the zeros, at least 60% of the total number are on the critical line. So anyway, yeah, and now we actually, it's actually sort of important in some ways that we have the analog of the BCHB conjecture, or that to get up to 60%, because our mollifier is now no longer just mu times a smooth thing. It's a more elaborate mollifier that Feng found back in around, oh shoot, I can't remember when that was, 2007 or something? No. Yeah, anyway, it's a more elaborate mollifier that it's kind of like you're doing Levinson's method. So you're integrating not really just zeta, but like zeta prime or some linear combination of derivatives of zeta, and not on the half line, but slightly to the right of the half line, you know, one half plus some constant over log t. And so now if you think your mollifier is trying to be the inverse of the thing, some partial sum, some smooth partial sum of the inverse of the thing you're trying to mollify, well then it's no longer just mu. You're taking, you want to know kind of, well, what's the inverse of, zeta plus 1 over log times zeta prime plus 1 over log squared times zeta double prime times some constant, etc. And you find that it's not just Mobius, but sort of, sort of a convolution of, or maybe a convolution of a couple of Mobiuses, something or other like that. And so it's not quite so clear how, about the theta equals infinity conjecture and things like that. And so a lot of stuff doesn't quite work. And so we really did want to have to be able to use Feng's mollifier to have general arbitrary coefficients in this formula. And so then that gives us up to the 60%. And by the way, even I think this is true, that one ought to be able to go up to, even with Feng's mollifier, one ought to be able to go up to m equals t to the 4/7, which I believe would give an improvement even over that 5/12. I have to check, but I think that's right. So I don't think in the 5/12 result that I mentioned of Pratt and Robles and Zaharescu and Zeinler that they are taking a mollifier of length t to the 4/7. I think it's slightly shorter, but I could be wrong about that. Anyway, okay, so now these twisted moments, there's a couple, there's sort of a few other reasons I'm interested in them. I mean, they're obviously very useful for applications. I hopefully made that clear. But they're really important kind of structurally as well. And there's some funny things that go on. And so I want to kind of explore those themes a little bit. And one is that you can sometimes get kind of exact formulas for some of these twisted moments, which is a little bit surprising maybe. And excuse me. Two is that sometimes you get kind of a reciprocity formula, which is kind of completely unexpected. It's not something that's not obvious at all from the original structure of the problem. And so there are, I don't know, a couple of examples where that actually happens, and where that might, well, it's already been useful, but it's not. I think we don't really understand exactly how useful it could be. And so I think that's something worth keeping in mind. And so anyway, so I want to go back to this work of Balizard and Sayas, which really is sort of translating into what I would call sort of classical analytic number theory, an equivalent that Berling found for the RH. Okay, so basically they kind of take a Mellon transform of Berling's stuff and come up with this. And I have to say, before I saw what Balazard and Sayes had done, I wasn't that interested in Berling's equivalent, but with the Balazard Sayes thing, it made it look like, well, you just need to mollify zeta in a really good way, and then you're all set. And there was an important piece in that by Baez Duarte that made Berling's stuff, the support sort of the test functions in Berling's work go to, I don't know, integers instead of real numbers. But yeah, anyway. And then Väsyunen gave a really nice formula for an exact formula for the integral that they have to evaluate. And so that's the first example of sort of an exact thing. And then Sandro and I found a reciprocity formula for this, which is sort of an unexpected relationship then between sort of the twists of zeta by m over n and by n bar over m, where n bar is the inverse of m. So let me sort of explain that. Okay, so here's Väsyunen's formula. So he has this this sum V of HK. Here are the double brackets. Oops, wait a second. Double bracket X is just X minus integer. Wait, is that what it is? Or maybe with minus a half? I forget now. Sorry. Maybe, oh yeah, sorry, I forgot. Okay, maybe with a minus a half. Yeah, otherwise it would just be fractional part. Yeah, I think it's X minus. Okay, anyway, so you have this sum, and it kind of looks like a Dedekind sum, right? If you had a Dedekind sum, you would either have both of your arguments would be in the double parentheses, or else both would be cotangents. Okay, well, here you have one sort of double parenthesis and one cotangent. Anyway, that's a Väsyunen sum. And here's the twisted moment of zeta that's in question. It's a little bit different from what we're normally looking at. We're usually focusing on the interval from 0 to capital T, whereas this, because of this weight here, really sort of focuses on, well, what's happening down near 0 in some sense. But nevertheless, it's a twisted weighted average of zeta. It's twisted by h over k to the IT. And Väsyunen proved really a beautiful formula that, in fact, a beautiful exact formula for that twisted average. And that's this here. So that's quite nice. And the connection, the Balazard-Sayes connection to the Riemann hypothesis is that RH is true if and only if this limit is 0, where you take the inf over Dirichlet polynomials of length n. I know I switched from n to. You take Dirichlet polynomials of length n and try to make the average of 1 minus zeta times that polynomial, the mean square of that with this weighting function, make that as small as you can. Make that, yeah. And so that is, if you can do that, then you get RH, and now you've got an exact form. If you expand out this, square out the integral and just integrate term by term, and then use Väsyunen's formula, then you just have the simple bilinear form that you have to prove has coefficient that you can make go to 0, and you're done. Nothing to it. Okay, well, it's not quite that simple, but okay, but so then Sandra and I found a reciprocity formula, which is on this slide. So this is with Sandra Bettine and me. And so we sort of switch the where the H is, right? In VHK, you had the H back over here with a double parentheses, but if you put the H over on the cotangent, that can be accomplished just by a change of variable. A goes to A H bar, and then you can remove the double parentheses because A over K is smaller than 1. And so this is a thing we call C of HK. So also kind of looks like a Dedekind sum, but it's just, yeah, it's just minus V of H bar K. And what we discovered is that, well, what we discovered is this, that C of HK times H over K plus C of KH minus 1 over pi K minus log of H over K is an entire function of H over K. So so that was quite surprising and unexpected that happens. And of course, we were very excited about it because we thought, well, this is going to, open the door for proving RH. We just need to figure out how to use this in that Balzard-Sayes example, but it didn't quite work that way. Yeah, so anyway, this G of Z has this expansion with G of N's being pretty small. And we did find some nice applications of this. One is to a Voronoi formula, kind of a generalized Voronoi formula that allows your test function to have support at the sort of at the origin. And so we like that. Here's an example. In the case that, say, Z is 1 minus e to the minus delta. So that's around, that's around I delta, I guess. We have this where this is, there's asymptotic formulas, right? So then you'd be looking at an asymptotic formula for summation D of N e to the minus N delta. And you can write out an asymptotic series for that, but it's a divergent asymptotic series, right? In powers of delta. But this is an exact formula that converges very nicely everywhere. This term here is like summation D of N e to the minus N over delta. And delta is small, so N over delta is huge. So that converges super fast. And this thing, the coefficients C of N, again, are small, e to the minus square root of N. And so here, this gives an exact formula for an exact sort of Voronoi formula that's convergent in a region where the usual Voronoi is not. We use that to give an exact formula for zeta, now weighted in such a way that the mass you're looking at is at sort of 1 over delta. This is the W delta T is like an e to the minus delta T. And again, you get a formula that it's an exact formula that converges quickly, can be calculated super quickly. These U's are Chebyshev polynomials. The point of the AMs are really small, so this all converges, everything all converges here super quick. So you can actually calculate that very quickly. Okay, so now I want to turn to, let's see how we're doing. Okay, mean square of Dirichlet functions. Okay, so twists of the family of Dirichlet functions. So when we were looking at moments of general families, I was trying to look for error terms and make sure that sort of the recipe thing that we had found kind of worked in all the families that I knew. And so I was looking at just a family of mean square of Dirichlet functions. And so studying Heath Brown's paper, now he'd given an average, an asymptotic average actually using that formula for d of n e to the minus n delta, but the asymptotic formula. But it was for all. And when I restricted to primitive ones, then it got a little bit more interesting. And I actually found a kind of reciprocity formula for twisted L functions. And then Matt Young refined it, and then Sandro sort of turned it into an exact formula. So here's sort of the original reciprocity formula that I found. We're averaging L1/2 chi squared times chi of A. We call that MAQ. Now this is scaled a little bit differently. It's scaled with a kind of a 1/√Q scaling. Okay, so the size of it is going to be around root Q or so. Anyway, here's the reciprocity formula. If you take MAQ minus M minus QA, then you get sort of all this main term. And this gives an asymptotic formula that goes beyond the range of what you would normally get for this. Here you would expect the asymptotic formula to only work for A up to square root of Q. But in fact, if you take both of them together, then you can get A up to Q to the 2/3. And so it kind of extends the range of what you know about that twist by including sort of the other term. And then Matt made it much more precise. And if you write his exact formula, if you write his error term like that, just if you calculate his error term, you see that it kind of looks sort of interesting. This is, yeah. And in fact, then Sandro showed that error term is in fact a continuous function. E of A over Q is actually, E of A comma Q is actually E of A over Q is a continuous function. And I think I'm going to skip through this a little quickly, but he gave an exact formula for, so MJ star is sum over chi mod Q twisted by chi of A, but not just at 1/2, but it's actually a sum of L, but at half minus J and half plus J, with an extra sort of zeta term added in here. And well, this is a little complicated, but anyway, he gave an exact formula for M0 here, which is kind of nice. But one of the things, sorry, I know I'm just sort of skipping through that, but one of the things is that in this reciprocity formula, you can sort of repeat it. You're looking at MAQ, and then that gets related to MQA or maybe M minus QA, but then you can reduce Q mod A, right? Because it's just a chi of Q, but chi mod A. And oh, by the way, Q is supposed to be prime and A was supposed to be prime in those previous slides. And then you can apply the reciprocity formula again. So you go back and forth, you keep on reducing the thing, like the Euclidean algorithm or something. And so in fact, this second twisted moment of L, Sandro writes in terms of the continued fraction of A over Q. If the Vj is the jth partial denominator, then you get an exact formula like this. And that then, one of the things that, so that's interesting, and it would be really interesting to try and apply this sort of further. But one of the things that comes out of this is that you can actually then see when M0AQ might be particularly large. So it kind of explains a little bit of this thing where you see sort of the large values that kind of occur when A over Q is close to a fraction with a small denominator. So that sort of aspect of it can be made sort of explicit from this continued fraction expansion. And in fact, it shows that, yeah, so here's a nice sort of clean formula for this in terms of continued fraction expansions. And it shows when this thing is large. And so one of the points is that, so point-wise for individual A, you can't really the thing is, does not behave as well as you might like. So restrictions that sort of came from looking at this thing individually, it turns out you can be, well, if you put in general coefficients and average, then on average, the terms are small, but there's some individual ones that are quite large, is what I'm trying to say. So yeah, I didn't say that very well, but so this can be used to analyze especially large values of these twists. And the large values are much larger than the individual large values are much larger than when you average over all twists, like put in a polynomial and do sum over chi L half chi squared times a polynomial squared, then you get much better. I mean, I guess we sort of knew that, but this this sort of really brings it home that that's a phenomenon. Okay. All right. Well, okay. So quadratic L functions. So Sound gave a formula for that. He was studying non-vanishing of these of quadratic L functions at 1/2. That was sort of the Challa conjecture. That these L functions, quadratic L functions never vanish at 1/2. I think, yeah, and I mean, in general, we don't think any Dirichlet L functions vanish at 1/2. I don't know, I can't remember if that was part of Challa's conjecture or not, but certainly the quadratic ones. And Sound proved at least 7/8 of these don't vanish. And then he and I used later on these twisted L functions, but with shifts and things like that, to show that in fact, for 1/5 of quadratic L functions, you don't get any zeros, any real zeros to the right, any positive real zeros of the L functions. Yeah. Right. Okay. Let's see. So what time should I be stopping here? At 50 past, or what? What do you recommend? Somebody, Kaisa?
Well, I think it's okay if you go until 5 to 55, and then there's
55.
time for a couple of questions after that.
Okay. All right. Well, all right. So yeah. So in general, so we have a recipe for moments of L functions, basically in any family. And there's an analogous twisted recipe that's not really written down anywhere. And it's just sort of still coming into shapes, still being formed in some sense. And one of the issues is not quite sure what error term we should expect, especially as a function of the twist. But here's a recipe for moments of quadratic, for quadratic L functions. Well, twisted, this should be, yeah, so LA S chi D is a product of L of S plus alpha chi D over alpha in A. A is some set. So it's just a product of all those. And then we have a smooth test function, and then that product, and then we're twisting by chi DL. So if L is 1, then we're not twisting. And in order to write down sort of what the recipe is, it turns out this is the critical function here. Some n equals square tau a n over root n. Of course, I could just put in m squared here, but I like to write it this way because then in fact, when we twist it, you don't have to change the function very much. And so the critical function when you're twisting is some, well, n and d are coprime, and then n times L is a square. So when you twist, the way that you change the basic function is you include this condition, not just n equals square, but n times L equals square. So it's a pretty seemingly kind of minor thing. And then this is the recipe that we have, that if you average this, then basically what you get is you get these swap terms. You get a sum over subsets of A, be a subset of A. These are the factors from the functional equation. And then here's your basic function, B super D of, now it's A, you take your set A, you throw out the elements B that's in your subset, and you add back in the negatives. So you replace all the things in B by their negative. That's what this A minus B plus B super minus is. And we conjecture an error term, L to the 1/2 D to the 1 minus delta. This we're not so sure about what that should be exactly. For zeta, we would have put out D to the 1/2 plus epsilon there. But for quadratic L functions, there's some extra terms that can come into this, as discovered by the multiple Dirichlet series people, Diaconou and Zhang and Hofstein, and yeah, anyway. Okay, so with Brad Rogers, we proved this basically in the situation where we replace our quadratic L functions by a partial sum, a sum up to n, where n is d to the eta, and eta can go all the way up to 2. And we get the exact analog, assuming the Lindelof. We basically proved that twisted formula. So that actually works. Okay, sorry, trying to keep track here. Okay, right. There's an exact formula Ivanets and Sarnak found for twists of orthogonal L functions. Kowalski, Michel, and Vanderkam have studied this for the 4th moment case. And then recently, Blomer and Kahn found a very exotic reciprocity formula for twisted 4th moments here. So I won't describe that. But I wanted to just mention, if I can first, what happens in the random matrix case. So this is the recipe for zeta, and you have this basic function here for twisted zeta. Oh, right, twisted zeta, that's here. Oh, I see, okay. So sorry, those guys weren't supposed to be there. Yeah, that's a basic function for zeta. And then for twisted zeta, you just have to change your condition a little bit to that. And in random matrix theory, what we found is, well, if you take, the coefficients for characteristic polynomials, if you call those the secular coefficients, then what Sig Balu and I found was a formula for twisted moments in random matrix theory, twisted by these secular coefficients. And the thing is that it comes out a very nice analog with what you have for the Riemann zeta function case. We have this analog of the tau function that we define for random matrix theory. And when you twist, you get sort of this function, which involves sort of multiplying by the taus, which is kind of like what happened. Oops. Oh, I guess that's on the next slide. Sorry. What happened here, the BMN. So yeah, so trying to compare those two things. And we're trying to make this, we're trying to take this a step further and have a random matrix version of sort of the papers that Keating and I have been working on that give an approach to the general recipe from convolving twisted recipes together. And that's where we're sort of headed. Okay, thank you. Happy birthday, Balu. Happy birthday tomorrow. Thank you.
Thank you very much for this interesting talk. If you have some questions or comments, please put your mic on and ask.
Hello, I have a question. So
Yeah.
in the modification, of zeta function, you consider basically your modifier square and so zeta even zeta square. So as you see the Selbach type modifier, they are basically modifier power 4.
Right.
So this case actually I did not find anywhere the asymptotic result. So can you say something?
Right. So yeah, you can work all that out. And I tried to do that at one point. I think you get slightly worse results, but they're not quite as bad as sort of has been reported. I think in Selberg's, proportion of zeros on the half line. I mean, somehow by having to do a fourth power, it sort of ties your hands behind your back a little bit and restricts what you can do. But I think you still get decent results. I don't know if that answers your question, but yeah, you can do that.
So in this case, the modifier, heard about the modifier length?
Oh, you should be able to get the, oh, can you go longer with that modifier? I do not, yeah, I do not know. I mean, Desier Ibanez look at that zeta squared times a product of 2 squares of modifiers. Yeah, no, I have not thought about that. I don't know.
No, thanks. So another question, sorry. If you saying about this reciprocity law for these central values twisted by character, so if you consider the your cast form case, I mean degree 2 setting, and if you similar type of study, the this reciprocity formula holds for degree 2 setting.
In the for orthogonal twisting, is that what you said?
Yeah, I'm saying yes. I mean, you mentioned already initially the F belongs to HKQ and L half F power 2 lambda FL.
Right. So yeah, so I don't know. I mean, yeah, I was curious about that when I was preparing this talk. Okay. But yeah, so the Ivanit-Sarnak is for level 1. They mentioned something about level Q, but they never mentioned a reciprocity formula. And so, you know, Blomer and Kahn get it for 4th power. So I don't know. It seems like there ought to be one. There might be, and especially since Ivanit-Sarnak have an exact formula. So yeah, I mean, I think that would be worth doing for somebody to do yeah, twisted mean square. Is that's what you're asking about?
Yes.
Yeah, as far as I know, nobody's done that.
Oh, thank you very much for your nice and informative talks.
You're welcome.
Does somebody have a short question?
Yeah, your work with Bettine, you talked about these L1/2 chi value squared times chi of A, and its size depends on the continued fraction of A over Q. How do we interpret that? What does that tell you about the size of L1/2 chi's?
Well, I think, yeah, so, so Sandro explains it pretty well in his paper. It's a very nicely written paper. I recommend it, a transactions thing. But basically, when you have a large denominator or when you have a large convergent, I guess, that was right. Yeah, in the continued fraction expansion, then you're going to get a large, I may not be saying that right, but it's something to do with, yeah, getting a large convergent or a large, whatever in the continued fraction that would give you a large value of that twist.
Right now, I'm just wondering what does it say about the L function values? It's some strange sum that is controlled by a continued fraction, but the natural thing to ask is the size of L1/2 chi.
Right, but if you have right, so I guess if you twist by chi of A and A over Q is close to, yeah. Yeah, I don't know. I would say go back and look at, you know, Polya Vinogradov, where you expand partial, well, maybe that's not right. Yeah, I don't know. I don't have a good answer for you.
Fair enough.
Okay, let's thank Brian again now.
Okay, thank you. Pi Day. Yeah, today's Pi Day, right? And something else, right? Okay, thank you. I should stop sharing, right?
I think we can continue, say, in 4 minutes so that there's time to set up and stuff. So let's continue 5 or 35 past, depending on where you are. So in 4 minutes. Okay, I guess you are ready, but I think we can still wait for a couple of minutes if somebody wants to get coffee or something. So in between the talks.
Okay, ready?
Yeah, my time is 5 past. Are you ready, Andrew?
Uh-huh.
Are you ready to go?
Mhm.
Are you ready to go?
Yes, I am. Yes.
Okay. So it's great pleasure to introduce Andrew Granville from Université de Montréal, who will talk about primes in short intervals, heuristics, and calculations. Okay.
Thanks, Kaiser. I just wanted to start off by saying thank you for organizing this conference, but it's a great shame we couldn't come to Chennai. I'll just show you what it's like after 3 months of winter in Canada. I hope you can see. Yeah, it's probably a little different from what it looks like in Chennai, I'm guessing. I think I saw you at 28 degrees, even though you're in the evening. We're at -6, so which is a warm day for now. Anyway, it's a pleasure to speak today. This is joint work with Alyssa Lumley, who is a postdoc here in Montreal, as well as being my first mathematical granddaughter. So yeah, so this seems like a conference, lots of interesting people. One thing I wanted to mention was there's been a sad loss is happening. There we go. Unfortunately, Alexander Ivic passed away 3 months ago. So this talk's dedicated to his memory. Okay, so we'll start with Gauss. Where else? And as a 16-year-old, he studied tables of primes. And he guessed that from his studies that the density of primes around X is about 1 over log X, which suggests that if you're looking in short intervals, that you should have about Y over log X primes. But you have to temper that a little bit by saying, when does that actually make any sense at all? So obviously, if Y is 1 or 2, you're not going to have 1 over log X prime, so it doesn't make much sense. If log X is some power bigger than 1, then at least it's sensible. You've got some sort of asymptotic formula, perhaps. If Y is, say, a half log X, I don't, what does it mean? So, and okay, so maybe if you make sense of this statement, you still have to ask, is it true? So, yeah, so let me just start with what we kind of know. And this is a talk mostly about conjectures and heuristics. So I'm not going to worry too much about assuming things. So in 19, if you have lengths that are bigger than about log squared, then you should you do almost always get squared goes in. The number of primes in interval of length Y around X is about Y over log X, but that's true for almost all X, which doesn't mean all. It's obviously a probabilistic statement, which means the proportion of intervals for which this is true tends to 1, but there may be exceptions. And in fact, there are exceptions. So Selberg had shown in RH that this is true. But in 1984, Meyer showed there are exceptions when Y is any fixed power of log. So it could be, say, log cubed or log to 100. And what he showed is that if you take an interval, so it's a bit full of notation here, but if you take an interval between X and X plus, say, log X to the 100, then what the Selberg had said in most intervals, you get log X to the 99 primes. But what Meyer shows is that you can get slightly more, 1 plus some little delta, and you can get intervals that have got slightly less. These are exceptional intervals, but they do exist. And this constant is quite small. So if A was 100, we'd be talking about, what, 1 over 10 to the 200, roughly, as constant. So very, very small. But nonetheless, you don't get the asymptotic. Okay, so what I'm going to be interested in this talk primarily are the maximum, minimum number of primes you can get in a lengthwise subinterval between X and 2X. So capital M will be maximum, little m will be minimum. I'll primarily focus on maximum, which is a strangely there's not a lot of literature on this, strangely. I guess partly because we can't prove very much. So we do believe that if Y is in this range that Selberg looked at, if Y is bigger than log squared X significantly, if Y over log squared X goes to infinity, then the number of primes in an interval of length. So the minimum is bigger than some constant times Y over log X, and the maximum is less than some constant times Y over log X. When Y is smaller, this lower bound may be wrong, but we want to investigate. So basically, when I'm in this talk, I'm thinking of when Y over log squared X goes to infinity, this is sort of in the understanding that we have in the literature, even though there's only a few results like Selberg's and Meyer's. But what I want to do is start looking at smaller intervals, shorter intervals. So let's just look at the number of primes between X and X plus Y. And one way to do it is to simply remove, to at least get an upper bound, I can, well, obviously integers that are primes between X and X plus Y have no prime factors less than root X. So I could just start sieving with the small primes. So I certainly get an upper bound that the number of primes between X and X plus Y is no more than the number of integers that have got no prime factors less than Z in that interval where Z is less than or equal to X. So just standard notation, we'll use p to be the product of the primes up to z, and sxyz will be the number of integers between x plus 1 and x plus y, which are coprime to the product of the primes up to z. So we can sort of optimize this in terms of sieving. I mean, we would want to take z up to root x, but in practice in sieving, you're not going to be able to sieve with primes longer than the length of the interval, probably less than that, but the length of the interval would be a miracle. So the best bound we can get from just this trivial observation is that the maximum number of primes is the worst case of sieving an interval of length y if all the primes up to y. And I claim that this is the size of the largest admissible set of size y. So let me remind you of what that is. So Hardy-Littlewood's prime k tuples conjecture says if you take any k integers, which are admissible, I'll explain that in a second, then there are infinitely many n such that n plus a1 up to n plus ak are all primes. Now, this is obviously nonsense for, say, n and n plus 1, because you've always got something divisible by 2, or n plus 2, n plus 2, and n plus 4, because you've always got something divisible by 3. So as long as you can avoid any local obstruction, then, well, that's what an admissible set is. It's a set of integers like a1 to ak that has no local obstruction. And then we believe that infinitely often these guys will all be prime. And what I need to do is be a little more specific about infinitely often, but let's do that in a second. So this set has size k, well, there's k integers, and length y, because the gap between the smallest and largest of the AIs. And sy is the largest size of an admissible set of length y. And what we just said was, if you look at the primes in an interval of length y beyond x, then you can sieve out for primes less than or equal to y, which leaves you with that it's no more than the size of the largest admissible set. So, but here is a sort of a key point is, let's suppose we had a admissible set of size sy. I mean, obviously we do, because the definition is it's the largest size of an admissible set. And so we've got some a1 to ak, which is an admissible set, and its length is no more than y. And let's just suppose we have such a k tuple between x and 2x, then, okay, we've got an interval that's got this many primes in it that's of length y. So the maximum is, so we have this inequality that the most primes you can have an interval length y is no more than the size of the largest admissible set of length y. And what we've shown is if you do get a prime k tuple in this interval, then actually you get equality here, maybe a little surprisingly. So what we want to do, if we want to understand this, is to try and understand when do we believe we'll get prime k tuples between x and 2x. So there's a quantitative form of the prime k tuples conjecture due to Hardy and Littlewood. And so we believe that the number of k tuples up to x is roughly this strange formula. So let's just review it briefly. So we're going up to x as x integers. We have, well, k numbers we want to be prime, and Gauss's heuristic, or Gauss's observation, was each of these is prime probability about 1 over log. So if they're independent, we'd have x over log x to the k. But they're not independent. We got to worry about maybe there's an odd one and an even one, so they couldn't all be simultaneously prime. So we need to take that into account. So what we do is that at each prime, we look at this locally and see how many n could you possibly have that these are all co-prime to the given prime p, and compare that to when they're independent. So when they're independent, the probability that p doesn't divide n plus a1 is 1 minus 1 over p. And then there's k of them, so that would be the independent probability. And now we want to replace that by the dependent probability. And that's just, well, it's simple enough when you think it through. It's 1 minus omega p over p, where omega p is the number of n where p divides this product. So what I want to understand is, well, this is an asymptotic formula in Hardy and Littlewood's work. They ask, when does this, eventually this should be about the right number of primes, up to number of prime k tuples up to x. But what we're asking here is when at what value of x is this starting to really be the truth? And I guess, one thought is when this formula is bigger than 1, then it may well be that it starts to recognize primes. I mean, for x very small, it's unlikely to be bigger than 1. But okay, so when we count primes or prime k tuples, we probably expect an error term of like x to the half. Now, to study something with such a good error term, you need to change the main term to be the integral dt over log t to the k, like you do in the prime number theorem. But we would expect an error term of something like x to the half. So what you could argue the right question is, when is this main term bigger than x to the half plus epsilon? So this is all very speculative. This should be the first x at which we steal prime k tuples, but I mean, you've got to guess something. So yeah, so I'll get on to trying to answer these questions in a second. Let me just now ask about the number k. I'm going to need to know its size in order to investigate this. So remember, we look at admissible set of length y. So what I want to do is understand this. How is k, the largest admissible set of length y, what is k as a function of y? So the Brun-Titchmarsh theorem in the Selberg-Montgomery-Vaughan version gives you that the number of primes in interval length y, or the number of integers sieved by, if you take an interval length y and sieve up to about y to the half, remember if Selberg does y to the half times maybe a little bit, then he gets an upper bound of 2 y over log y. And this is the best result. Well, more or less. You can put, I think, a log y plus a constant in the denominator. In fact, I think Selberg does that, or he could have done that had he wanted with his proof. And it's easy enough to get an admissible set that's bigger than y over log y. You just take the primes between y and 2y. Well, to see it's an admissible set, those primes are not divisible by any prime less than y. So you get your sort of admissible congruence class for every prime less than y. There's less than y of them. So for every prime greater than y, there must be a free residue class. And then if I want to put them in the interval between 0 and y, I just subtract y. I think the biggest set known, I think Kevin Ford mentioned during a talk earlier that this has recently been improved, but by Koniagin, but Koniagin, but just in the little O1 term. Okay, so there's a difference between the best upper bound known and the best lower bound known. And we believe that the right answer is y over log y. This is open and one of the great questions, I guess, in sieve theory or analytic number theory. And we do understand why this is a hard problem, because if we wanted to improve as 2 in the upper bound, you would have to show there are no Siegel zeros. It's almost equivalent to that. So yeah, we know this is going to be a tough problem to beat this too. Okay, so now let's just, what we want to keep in mind is that the size of the largest admissible set, Sy, is somewhere between y over log y and 2y over log y, but we'll assume roughly y over log y. And what I'm interested in is the size of its Euler product, which came up in the Hardy-Littlewood formula. And basically, it's not really a very difficult calculation that you just split into ranges and think about the size of the things, and you can prove this. So the dominant term is log k to the k, and the log k to the k just comes from the product of the primes up to k from this first term. So if you substitute, so remember the Hardy-Littlewood formula was this times x over log x to the k. So if I substitute this approximation in, I get x over log x to the k times this thing. Instead of e to the 1, I call it c. Plus we expect, so this is kind of your main term size, and there's an error term size of x to the half. And so now you can just compare the two. And if I take x to be about k to the k, let's just plug it in. If I take x as k to the k, I get a k log k in the denominator, the logs cancel. So this thing becomes something like 1 over k to the k. Here I've got a k to the k. So that means this around this size, this main term is at least 1. And well, just think, when I think it through, if k is y over log y, this is like e to the y. In other words, y is less than log x. So the main term in this formula should be greater than 1 if y is less than log x. And if we want this to be as big as x to the half, then actually you need x bigger than k to the 2k or y less than a half log x. So this is perhaps a little surprising. So let me just review what we're saying here, because a few things happened. We're saying take the admissible k tuple of length y, which has as many things in as possible, the maximal one. And then we're guessing that we start seeing prime k tuplets pretty regularly once x is bigger than k to the k, or x is bigger than k to the 2k, if you want to be pedantic about beating the proposed error term. And then that, for this specific k tuple, that gives us these quantities. So let's see, this seems to suggest that the maximum number of primes you could get an interval of length y around x. We'll start seeing admissible k tuples that give you primes around between prime k tuples between x and 2x when y gets up to about log x, or just 1 minus epsilon times log x. Maybe a half minus, but I'm going to say 1. I'll tell you why I'm going to say 1, because I did that for one admissible k tuple, and maybe it works, maybe it doesn't. But actually, we don't need to work with one admissible k tuple. We could work with all of them. So on average, some k tuple just has to give you a prime k tuple when you get to that size. So we're going to conjecture that the most primes you can have in an interval of length y between x and 2x is the size of a maximum admissible set for y all the way up to 1 minus epsilon log x. And obviously, this is a bit of a risky conjecture. So how does it compare to data? So what we've done is try and collect data in ranges. I mean, it's quite a big calculation, because you kind of have to look at every interval and every admissible set. And anyway, there's a lot to do. So there's a limit to how far we can take the data. But here we're looking at x at 10 to the 11. So we're going to look at intervals between 10 to the 11 and 2 times 10 to the 11. And we're going to look at intervals of length y, and we're going to try and see what is the most primes you could get in there. So these purpley blue dots represent the most primes. So let's look at 30. So I'm looking at intervals of length 30 between 10 to the 11 and 2 times 10 to the 11. And the most primes I can get in such an interval is 8. We just computed all the intervals and looked. And then what I'm asking is the open square is what's the largest admissible set for y equals 30. And in fact, it has size 8. So what we find in this interval is that for intervals of length 30, the most primes you could get is actually the size of the largest admissible set of size of length 30. And okay, you can see for small y, this seems to work really well. And we've put a dot dashed line at logarithm. So for y up to log, it looks like this conjecture is true, that the most primes you can have in an interval length y between x and 2x is the size of the largest admissible set. And this actually seems to continue a bit beyond log. And then we start seeing it falling away. Well, that's kind of what you might expect, that at some point the admissible sets will get larger than the most primes you can get in such a length interval. And here's the data between 10 to the 12 and 2 times 10 to the 12. You can see it's very similar in its look. We get an exact hit well past log x, and then we start falling short. So we did 4 different intervals, 10 to the 9, 2 times 10 to the 9, 2 to the 10, 2 to the 11, 2 to the 12. Sorry, 10 to the 9, 10, 11, 12. And our data pretty much looked the same. We rather surprisingly got out to about 3 over 2 log x, it seems. This is a little beyond even. When we stopped having mxy equals s of y. I'm going to tell you that I don't believe that I think this is just small numbers, and that this is the right stopping point, and I'll explain that in a little bit. But yeah, so that's some data. Are there any questions at that point? Just very quiet here. Okay, so let me discuss in this conjecture that we believe that the maximal number of primes interval length y between x and 2x is the size of the largest admissible set for y up to log x. We just saw some computational evidence. We did a study of the range of uniformity of the prime k tuples conjecture, kind of best guess scenario, or optimistic guess scenario. And well, you can also actually take Gauss's observation, and Cramér created a probabilistic model for how to think about primes based on that. And using Cramér's argument, you can get the same thing. And if I have time, I'll get to that later. So I want to point out that, well, just at the top end of the range, when y is around log x, what we're saying is we think that the most number of primes you can get an interval length y is the size of the largest admissible set, which we think is about y over log y. And here y is log x, so that's about y over log x. So the most primes in an interval of length y between x and 2x should be about y over log x. And well, let's just remind us, what did we say about when y is up at log squared x? So at log squared x, the most primes you can get in interval length y is like y over log x. And actually this persists when y gets larger, right? We believe it's always like y over log x from y beyond about log squared. Whereas for smaller y, we get a very different function. Now, these are both linear functions in y, but they have quite different slopes. So somehow going up to or around log x, we get y over log x. But then after log squared x, it's a much less sharp slope. So one of the key things we want to understand is how does it transition between a slope of 1 over log and a slope of 1 over log. So let me just make some more observations on this. So what we said is that around log x, the most primes you can have an interval of length y is about y over log y, which is the same as log x over log x. Whereas at y equals log squared x, the most is about log x. So the amount it increases between log x and log squared x isn't very much. Let's just put that in context. So if I just look at y as different powers of logarithm, what's the most primes we expect in an interval of length 1? Well, 1. An interval of length log x, we just saw it should be the size of a maximum admissible set, more or less. At log squared x, we just sort of have classical analytic estimates, and we expect about log x squared. So what happens as we multiply y by log x? Over here, we're jumping by log x each time, a factor of log x. And essentially here, we're jumping by a factor of log x. But here, it slows down to a snail's pace. So it's very, very weird that when intervals go between log x and log squared x, the number of primes seems to increase so much less fast than any other transition. So what I want to look at is much more carefully what happens between log x and log squared x. What is the maximum number of primes you can get in an interval between log x of length, log x to the a, where a is between 1 and 2, something like this. And I'm going to give you a conjecture, and this is based on this Cramér model that I'll talk about a bit later, that for y is log x to the a, for a between 1 and 2, that the most primes you get in interval length log x to the a should be, well, this log x over log x again times 1 over 2 minus a. That's crazy. So remember, when we go log x, we sort of go up to log x, we're looking at y over log x. When a is bigger than 2, we're looking at, sorry, at the start, we're looking at y over log x for a less than 1. For a bigger than 2, we're looking at y over log x. So there's a linear in y. And now this function, if it makes any sense at all, is, wow, if you take y, a is something to do with a logarithm of y. So somehow we've got a function of a logarithm of y in that interval. I mean, I'm not saying it intuitively makes sense to me, except various things point to this. And I'll be a little more precise. If the length of our interval y is between log x and little o log x squared, then here's our function, log x. This is what comes out of what I think is a good probabilistic model. Log x over log of log squared x over y. So you can see as y gets up to log squared s, this starts to become a problem factor and things change. Things are going to be, it's going to be a clear transition point with that kind of function. So let's have a look at the data. Here's the conjecture. And yeah, so this is our conjecture, is the function L, what we believe is the right number of, the maximum number of primes. So if I look at, in this interval between 10 to the 11, 2 times 10 to the 11, I look at intervals of length 150. Here's what we're predicting is the most primes you can get in such an interval. And here's what the data told us. And okay, it's not a bad fit, right? So let me show you 10 to the 12 as well. It's also not a bad fit. It's very similar looking, right? The data and the conjecture are not that far apart. What's weird is our conjecture is kind of concave up and the data is kind of concave down. I have no idea why, absolutely no idea. So the first thought would be there's a secondary term that's missing that might explain this, but when we put in the secondary term, it doesn't seem to do very much. So yeah, I don't know, just don't know. Okay, so this maximum number of primes in an interval of length y between x and 2x has, we're looking at 4 kind of ranges. We look firstly at y up to about log x. We've just looked at y between log x and little o of log squared x, and we said it around as y comes up to log squared x, there should be some sort of transition. And we looked earlier at y over log squared x goes to infinity, so we need to look at this range of y about log squared x. I only talked so far about the maximum. Let me just say a few words about the minimum. For y up to about little o of log squared x, we expect that there are intervals with no primes in them. So the minimum wasn't very interesting in these first 2 ranges. And in this range, we said we think mxy is bigger than y over log x. So the minimum's most interesting, I guess, here, especially when it stops being 0. So let's go to that third range. And I'm afraid it's a bit complicated, but this is what comes out of the appropriate calculation, that if the length of the interval is a constant times log squared x, or I call t the constant, then the maximum number of primes we believe is, well, this strange function u plus, and it's u plus of c times t, where u comes out of some equation, which it's a derived function, and this comes out of an entropy calculation, which is a fancy way for saying when you make some binomial coefficients equal to what you want them to be equal to. More interesting is what is C plus, and C plus is some sieving constant, and I will explain later what that is. But all we know is the sieving constant, all we can prove is it's bigger than 1.015, and we don't actually know its value. So that's the conjecture for y like a constant times log squared x. And I'm being very inexplicit, but in some ways it doesn't matter. I just want to look at the data. Oh, I should say we conjecture perhaps that this lower bound that we have is correct. I don't know if it is or isn't, but at the very least, to create data, we need to make an assumption. So we'll just take the constant as if it's what's known as the lower bound. So here we are. Here we're comparing now in sort of constant times log squared x length intervals, what our prediction gives, which is the pinky line, to what the data says. And you can see we're a long way out now. We're substantially 25, 30% larger. Maybe that's a bit more, it's a bit less than that. But here's 10 to the 12 and 10 to the 11, 10 to the 12. You can see very, very similar pictures. So we're really out a bit. Yeah, so prediction, oh, I did do the calculation, I guess. Towards the end here, it's out by 35%, so that's pretty horrible. Let's just do the same calculations with minimum, now that minimum might be interesting. And it turns out you also want to look at the same equation to derive a guess. There's also a sifting constant involved. And this minimum, remember before we had u plus c plus t log x. And well, this is perhaps a more familiar sieving constant. The c minus is less than e to the gamma. I'll explain the relevance of a sieving constants in a minute. So let's have a look at this compared to, oh, and again, to compare to something, we're just going to assume this is best possible. There's some recent work of Banks, Ford, and Tao where they make some claims that seem to suggest they think this is the best possible, but I don't really know what to believe. Okay, so here's our data. Here's our belief that the minimum of a number of primes. So for instance, here's an interval length of 1,000 at around 10 to the 11. We're looking at the least primes you can get an interval length of 1,000. Here's the number, which is about 10, I guess. And our guess would be about 2.5. So horribly wrong here. I mean, the most interesting point really is, when does it stop being 0? When are you guaranteed that there are primes in every interval of length t log squared x? So this seems to come off from being 0 at about 3/4 log squared in practice. And our prediction is way, way beyond that. It's about 1.1 log squared x. I'll explain why in a minute. And here's the 10 to the 12 data. You can see it's very, very similar. This is pushed beyond 3/4 there. So if you look at the data for 10 to 9, 10 to 10, 10 to 11, 10 to 12, this number does slowly push beyond 3/4 log squared x, but it's pretty much around there. I'll put everything on the same graph. So you can see this is kind of the mean number of primes in an interval. And this is the maximum and minimum from the data. And here's our predictions. I guess the minimum in this graph looks a little closer than the maximum, but we're still a long way out, clearly, from some. So basically, we don't know whether the heuristic basis for these predictions is wrong, or whether it's just the data that comes from looking at small numbers. So maybe that these guys will meet and start looking the same out at 10 to the 100, but we have no way of knowing. So as I said, if the minimum is bigger than 0, then we're guaranteed there are pairs. Every interval of a certain length has a prime. So this tells us something about the largest gaps between consecutive primes. So we're interested when this minimum, its prediction, is bigger than 0. And so we just have to understand this function. And it turns out that's simply when the thing inside is bigger than 1. And so we have a conjecture for the maximal gap between consecutive primes. It's at least 2e to the minus gamma log squared x. The traditional conjecture of Cramér is 1 times log squared x. This heuristic reasoning gives us bigger than a constant, slightly bigger. I should say 2e to the minus gamma is like 1.15. So it's a little bit bigger than Cramér's conjecture. And it's possible that we have equality here. As I said, there is some conjecturing of that. So let's just have a look at the data. And here are the record-breaking gaps. Now remember, what I said is the maximal gap over log squared should be, well, Cramér said it should be heading to 1. We're conjecturing here it should be bigger than 1.15, and the data is not behaving. It's only got up to about 0.92. Oh, sorry, 1.12 is what 2e to the minus gamma is. So we're still in our regime where we really don't know whether the data is misleading us. Here we drew a graph, and the spots are the record-breaking maximums of Pn plus 1 minus Pn in each interval. And this is our prediction of 2e to the minus gamma in blue, which is way off. Here's Cramér's prediction of 1 times log squared, which is also way off. And when you do this heuristic, what you find is that there are a few things that are a bit hard to get your head around whether you should include them. There's certainly a log squared term, I think, times the 2e to the minus gamma. And there's probably other terms like log times log log and a log term. So I thought, well, why don't we just try and best fit? So we have a nice best fit formula. I mean, they're more or less this, 5 and 6 as coefficients. It looks brilliant compared to the data. but we have no reason to believe he's coefficients 5 or 6. So I'm not sure whether this is a good thing to include in a discussion, but maybe one can start trying to understand the reasons for these extra terms. We have reasons why we believe there are extra terms of that shape. It's just that the coefficients 5 and 6 come out of nowhere. Okay, so let me discuss the Gauss-Cramér heuristic. So Gauss, as I said, as a boy, made this observation. Cramér said, well, hey, why don't we model this by just taking independent random variables, xn, starting from 3, and we'll have a probability that you get a 1 is 1 over log, so like 1 over log there, and otherwise it's 0. And then what we're going to do is we're just going to look at sequences with this probability space and write down 1 or 0. And we'll think of, so for primes, the first 3, 5, 7, 11, this is the sequence of 1s and 0s that indicate the primes. And our guess is that whatever's true of probability 1 for these independent random variables will be true for the odd primes. This actually is what Cramér writes in his 1936 paper. And so, for example, you can show that the sum of these guys up to n looks like the logarithmic integral with a small error term. And so this Cramér hypothesis says you should guess that the number of primes up to n looks like logarithmic integral plus a nice error term. And of course, this is the same as equivalent to the Riemann hypothesis with this error term. So Cramér implies the Riemann hypothesis. For what we're doing, we're looking at integers between x and 2x. And so this 1 over log n is pretty much 1 over log x. It's a simplifying assumption, which means if so what am I doing? I'm looking at intervals from x plus 1 to x plus y. And I'm asking for how many primes are there in the interval. So the model, I want to look at this random variable, intervals from x plus 1 to x plus y, and ask how often they equal k. And if I can think of everything here as being independent and all the intervals being independent, then this is just a binomial coefficient calculation, right? I've got y choose k possible ways to get 1 in here. Every time I get a 1, it's a 1 over L to the k. Otherwise, it's a 1 minus 1 over L. So to understand things, I just have to play with this probability. My one issue is that when I'm looking for intervals of length y, I want them to be independent. So there's x intervals, but if I start an interval at t and I start an interval at t plus 1, they're not independent. So I might as well start at t plus y, t plus 2 y to make them independent. Then I only have x over y intervals, but given that y is so small, that's not going to affect the calculations. So for instance, to say, when do I have 0? What's the biggest y I can have to have 0 here? Well, if k was 0, the only term that survives is 1 minus 1 over L to the y. I compare it to the number of intervals, y to big O 1 over x. And that gives me, well, just a simple calculation, y about log squared. So this is Cramér's original argument. Yeah, so what I'm looking at here is intervals with short intervals with lots of primes. And if I take y as L over log L, then this is what I get. So what have I done here? I said there are intervals of length y with y primes in them, where y is L over log L. Well, L is log x. Well, that's stupid. You can't have a long interval where every number in it is a prime. Obviously, some things are divisible by 2. So this is a big problem of the Gauss-Cramér heuristic, is it works for some things, but not for others, because it would predict there's lots of primes in a suitably long short interval. It also, well, this is the more classical reason why people say it's a problem, is it doesn't know that 1 of n and n plus 1 is even, so it gives you infinitely many twin primes. So it's clear this model has a failing. It doesn't take account of small prime divisibility. So we need a fix. So where's the fix? Well, pre-sieve by the small primes. So if we're studying integers around x, let's remove integers that have a small prime factor less than log. And then hopefully this will adjust these issues. Certainly this issue about twin primes will disappear. We know about the divisibility by 2. So here we are. Here's the modified heuristic. You take the primes up to log x roughly and take the product. We're going to just say we know it's a composite number if it's got a small prime factor, so xn is 0. If that's not co-prime to the product that primes up to z. And otherwise, we define a sequence of independent random variables and we adjust for the small prime factors. Okay, so what the original Cramér model gave us was the prime number theorem, the Riemann hypothesis, primes in long enough intervals. It gave good predictions, but it failed on lots of other questions, but this doesn't. This new heuristic gives us prime number theorem for arithmetic progressions. It predicts a generalized Riemann hypothesis, gives us twin primes, it gives us prime K tuples, and it gives us primes in short intervals. At least it doesn't say anything that's incredibly inconsistent. Okay, so, okay, I guess I repeated that in the slide. But the interesting part is that the old model said that we should get the number of primes between x and x plus pi being y over log x whenever y is bigger than log squared x, and that was proved wrong by Helmut Mayer's calculations. And Mayer's idea actually depended on divisibility by small prime. So this new model actually takes account of Mayer's brilliant work, that it would predict what Mayer did, whereas the old model would not. So this gets us back to the sieving question. We're taking the integers between x plus 1, x plus y. We're looking at how many are left unsieved, and that's what we have to work with to apply a probability model, right? First, we sieve out the integers with small prime factors. Then we ask, using our model, whether we've got primes in there. So typically, here we're looking at an interval of length log x to the a, and I'm taking z around log x. And well, this is obviously everybody knows this, that the number of integers in interval of length y that are left unsieved is about this. That's what you expect. And Mayer's idea used the small and large values of this ratio, so that it could be less than and greater than 1. The sieve bounds that we're interested in is what's the most and the most and the least you can get for the number of integers left unsieved in interval length y by the primes up to z, compared to what you expect. And this is just, it's a sieve bound, but I'm only sieving intervals, which is a very important statement, because general sieve methods are looking at a different problem. They're looking at a more general problem. So yeah, we know it's easy enough to prove that these are the right sides of 1. And what does Mayer's proof actually give? There are some constants that come up, but what he really gets, minor modification, is the minimum number of primes is less than or equal to this sieving constant times y over log x, and the maximum is greater than or equal to this sieving constant times y over log x. So what I want to do is get the best possible sieving constants in for this ratio. And there is a general linear sieve problem, but that takes, if you like, what we do, sieving an interval, and creates hypotheses that are more general and, of course, work for many more problems. And these are the upper and lower bounds that Jürgen and Richard got, which are actually best possible. The problem, I mean, it's a wonderful piece of work, but the problem is they're not great for this problem because, for instance, this lower bound is 0 for all a greater than or less than or equal to 2. And I guess we don't really know how things compare. So what's the smallest? We know how to get sigma minus of 2. Now, this bound here is 0, but the smallest sieving an interval we know of gives us an e to the gamma over 2. And similarly, the largest sieving an interval we get at 2, so primes up to the square root, is 1.015. Those are the two constants you saw earlier. So yeah, so we have, for sieving intervals, we're asking a different question from the general linear sieve. So can we do better sieving intervals? Unfortunately, when working in this paper, I started thinking about this, and I was able to prove something very frustrating, which is if there are infinitely many Siegel zeros, this actually equals this, and this equals that for all A. So sieving intervals gets as bad as the general linear sieve if there are Siegel zeros. So Siebert had done something similar, but a little different. He looked at arithmetic progressions. I'm looking just at intervals. And anyway, so it's very frustrating. So without proving there are no single zeros, we can't improve on the general linear sieve bounds. So this modified Gauss-Cramer heuristic takes account of small prime factors, predicts most of the main conjectures and distribution of prime numbers theory. But to analyze it well, we'll need to resolve sieve problems that aren't fully resolved and can't be until we prove there are no single zeros, which is frustrating. So you gotta scream for that. So I guess the question is, can we even, so we've tested the predictions against data, but what I'm interested in is testing this modified Gauss-Cramer model against data. And to do that, we need to kind of go to a range where we can calculate the sieve problem itself, and then compare the data that comes out with a prediction of primes, given that we know the answer to the sieve problem. So here's some data. So we're looking at x is 10 to the 8. We're looking at intervals of length 340, which is about log squared x. I'm going to sieve with the primes up to 11. And first I need to know, well, in intervals of length 340, how many integers are left when I sieve with the primes up to 11? And it's somewhere between 68 and 73. So what I'm going to do is for each of 68, 69 up to 73, I'm going to look at the intervals where that's the number of integers left unsieved by the primes up to 11. And then I'm going to look at number of primes and then see how that fits. So we want to study distribution number of primes in the interval over all the values where we have exactly n numbers left unsieved by the primes up to 11. And here's the distribution. So the bars here, so here I've picked these intervals where 68 integers are left unsieved when we sieve with the primes up to 11. And for instance, here I'm looking at the number of such intervals who've got 20 primes left. That's this blue bar. And so there's like 100,000 of them. And we're comparing it to the prediction, which is, well, pretty much a bell curve. And let me just race through a few of these diagrams. Oops. So let's have a look. In these diagrams, what do you see? You see the red, the tip of the bell curve doesn't reach the height of the blues, right? It's definitely below. And this kind of reaches out further. So it's not a terrible approximation to the bell curve from the data, but it's got a lower height and it reaches out further. So it's not a terrible prediction, but it's not predicting correctly what seems to happen. So let's just have a look firstly at the means. Well, the means were pretty good, right? So these are the expected means from the random model. And for the number of primes in the intervals, say here of length, this is an interval, this looks at all intervals where 70 integers are left unsieved. And we're looking at the mean number of primes that are left, are in those intervals. And the actual mean is 17.96. The expected mean is 17.91. So that's really not bad. Let's have a look though at the variance. So now we should expect from what we saw visually, the variance to be different, because we saw that the prediction didn't seem to reach as high and it seemed to spread out more. So we could see on that data that the variance was bigger, that our prediction for the variance was bigger than the real variance, because our prediction spread out more. And when you look at this, our expected variance, well, they're all in the 13s, whereas the actual variance are kind of 10s and 11s. So that's something to be understood. And actually, it's understandable. So that was lucky. Montgomery and Sound did this extraordinary analysis of primes and short intervals by taking the circle method approach of Montgomery and Sound and estimating and guesstimating the many terms that appear, and rather beautifully. And what they were able to show was that one should expect that the variance looks like, well, y over log x, which you'd expect, times this weird function. Now, the point is, this is what comes out of the random model. So the y over log x times 1 minus log y over log x. Well, Montgomery and Sound have a couple of extra terms that appear. And when we actually just do the calculation with those extra terms, we get 11.11, and it's good. So although Montgomery and Sound's prediction is also a heuristic, because they make some guesses along the way, it's obviously nailing things pretty well. But the problem is, it doesn't really tell you the distribution function, this thing. Or what they prove, as you may know, is that, or prove modulo certain conjectures, that you get a normal distribution at the center of a distribution. But this isn't the question we're asking. We're asking what happens at the extremes, when's the maximum and the minimum? And I don't know how to convert their work into something that studies the extreme, even heuristically. Okay, so sorry, I'm just, I guess we started 5 minutes late. So one last idea is to try and ask these questions about large gaps between primes, but instead of using estimates for functions of prime numbers, since this is all numeric, do everything numerically, no kind of approximations. And so let me just, this is the last thing. So if I take log x to be 40, so I'm now looking at x between e to the 40 and 2 times e to the 40. Then the largest prime gap, oh, actually, I've just looked it up to x because that worked out more easily. The largest prime gap up to x is after this number, and it's 1248. And the Cranmere prediction would be 1600, and ours would be even worse, a factor of 2e to the minus gamma. So here's what I'm going to do. I'm going to take our prediction, I'm going to sit with the primes up to 20, and then I'm going to do things much more precisely. Like, for instance, remember I said L was log x, and then when we modify it, it would be phi p over log x. At some point in the calculation one did to make our predictions, we replaced this by this, but I'm not going to do that kind of thing. I'm going to stick with the most nasty things because I got a computer. So we got a prediction there of 1420. So it was quite a miraculous improvement over 1797 to 1420. It's not as small as the actual largest gap between primes, but it's certainly moved a long way from our earlier prediction. Gives us hope that what we're seeing that's wrong is an artifice that comes because we're approximating many things. So just to finish off, what if our R equals zeros? What does it tell us about the largest gap? And following the release of this preprint, Kevin Ford, like the next day, wrote to me and said, you know, if you think this through, you'll get, if there are infinitely many zeros, and the heuristic says that all of this is nonsense, that the largest gaps between consecutive primes is infinity times log squared. And if you work it out a little more precisely, if you have a C equals 0 at 1 over log q to the a for any a, then the largest gap between primes looks like log squared basically times log log. So yeah, so C equals zeros are a big problem with our understanding. Okay, I'll finish there.
Thank you very much. Are there some questions to Andrew? Brian, did you have a question? Oh, no.
No, I was trying to clap, but I raised my hand. I'm sorry.
Okay, okay.
Good job, Andrew.
Thanks.
So I have a question that's not very precise.
Sure.
So I guess there's a few quirks that we might expect things to be different for small numbers. So for example, the first zero of zeta on the critical line is fairly high, and so we might expect that to happen. Is there a way to say estimate when we might stop seeing the effect of for example, the smallest zero of the zeta function, and then we can know that, I mean, if that number is bigger than how far our computers can go, then we know that that's going to affect things? Or
well, I don't know that the smallest zero affects much here, but I don't know. So, but in general, can you say when small numbers are going to give way to the asymptotic? As you know, that's one of the big mysteries. I mean, some problems one has a handle on it. I'll tell you, there's a problem I thought about a lot for this very issue is on infinitely many Carmichael numbers. So I guess I think Kaiser, you have the best result. That is x to the third up to x Carmichael numbers, and you got somewhere around there. But
Harman has.
Harman. But you did narrow standard progressions, right? So
Yeah, exactly.
yeah. So when you get your computer out, and a lot of people compute it, especially these people who work at like defense agencies, they compute Carmichael numbers, and they've gone out so far, and they've never found more than x to the third up to x. And the conjecture, and it's almost certainly true because it's just standard analytic number theory conjectures, is there's more than x to the 1 minus epsilon Carmichael numbers up to x. So the calculations get to x to the third. The reality is x to the 1 minus epsilon. And I do actually have an explanation for that, which is that in that case, the calculations are not seeing what becomes a typical Carmichael number. So what becomes typical happens far, far later on, probably around 10 to the 100. So we're very unlikely to see in calculations getting close to x to the 1 minus epsilon. So I don't have any explanation here, but I do think that in some of these phenomena, what you have to look for is that what is typical of the phenomena is not necessarily what your data is computing yet. And so anyway, with Carmichael numbers, it worked out that there is a clear explanation that Pomerantz and I wrote a paper on. But here, I've absolutely no idea why this is the case. None.
Are there some other questions or comments to Andrew? Okay. If not, we can thank Andrew again. Okay, so I think it's time to conclude the evening or morning or whatever session, and we'll continue tomorrow. Thank you, everyone.
On behalf of the organizers, I would like to thank Professor Vatamaki for chairing the session, and also all the speakers today. Thank you. So we meet tomorrow.
Amen.
Bye.